Oh, I'm Brian Bush from the Marlowe team, and I'm going to talk a little bit about running Marlowe contracts on the blockchain. The previous lecture segment showed us how to simulate Marlowe contracts using the Marlowe CLI. Well, here we're going to use the CLI to run that same contract but actually submit transactions onto the blockchain. So we'll kind of pick up from where we left off. As you remember, we had a bunch of shell variables that were set to contract parameters, and we're going to carry over those from the previous lecture segment. Just to remind you, we had a 3 ADA minimum deposit, a 256 ADA price. Now, various transactions are also going to have some min ADA in them, and we're going to use 2 ADA for that. We had abbreviations for the roles involved. We had a bunch of time parameters, basically the deadlines in the contract. There was a roles currency that we used for the minting the tokens. This will be used on chain now with those tokens. And then token names are a concatenation of the roles currency, that policy ID, and then the actual name of the role. So we've got a bunch of stuff here. So we'll get started. And we also had a wallet that we had created in the lecture segment on installing Marlowe CLI. So we're just going to grab some data here. We're going to use the Marlowe Pioneers testnet, so its magic is 1567. And I have a Daedalus running right now, and so it has an internal node that's connected to that network. So we're kind of all set up with all these parameters. Now, because we have these different roles involved, we actually need to create signing keys and payment keys and addresses for them. So we're just going to go do that first for the mediator. And then we'll generate their keys and we'll print out the address. Once again, this is an address you could look up on the Blockchain Explorer for the Pioneers testnet. We'll do the same thing for the buyer and the same thing for the seller. So basically, these are brand new keys and addresses for these people. Previously, we had minted the role tokens. Now we're going to distribute them to the parties. So first we want to find out where they are, and we can see we've got this particular transaction that had the role tokens in it. I'm just going to copy and paste there. And the way to distribute the role tokens is just to create a simple transaction. You could do this in Cardano CLI, but we're going to use the Marlowe CLI version. Our main wallet is going to sign this, and we're going to consume all 4 UTXOs that are mentioned at the top here. All the change is going to go back to the wallet, and then we're going to send them each to the mediator, the buyer, and the seller, and they each get their 1 role token. We will not store a copy of this transaction in the file, and then we're going to wait 600 seconds for the tokens to be distributed. So these transactions take somewhere between 2 seconds and maybe 90 seconds in the worst case. So we have to be a little bit patient here. But basically right now we've submitted the transaction and we'll be waiting for its confirmation. Okay, there it's confirmed. We can see the transaction ID. And now we're going to actually clean up these wallets a little bit. So I'm just going to run 3 transactions. This Marlowe CLI clean tool basically reorganizes all the native tokens and collateral and things like that in a wallet just to make it easy to run scripts like this. It's not a critical thing. It just makes the scripting a little bit more convenient. So we see 2 of the transactions have been confirmed. Now the 3rd has been confirmed. So now we're going to make sure that we actually got these to the right place. And so the first thing we're going to do is, when we're using Cardano CLI, it actually outputs token names in hexadecimal. In Marlowe contracts, we tend to use ASCII text. So I just printed out a correspondence here. So CM as ASCII text, regular characters, is 434D in hexadecimal. Similarly with these other abbreviations. So when we query the blockchain at the mediator address, we see this token that ends in 434D. So this is exactly the CM token. Similarly, we can look at the buyer. We see 544D, which is right there. And then the seller, which is 4642. So it's up there. So this is a little bit inconvenient that in some cases we're using hexadecimal, in other cases we're using ASCII, but this is the correspondence. And then, so we got some copy and pasting to do here. So we're going to use these UTXOs. So the mediator, we're using that transaction, we're using the 0 as their plain ADA UTXO, and then using the first output as their second UTXO. And I'll put some quotes around this. Okay, and then the buyer is using that UTXO. And they're using the first index is pure ADA, and then, sorry, the 0th index is pure ADA. And the first index is the roll token. We'll be using these later. It's just convenient to kind of get organized at the beginning here. And similarly for the seller. And I forgot a quote somewhere. There we go. Okay, so we're just kind of recording this for future use. And then in the lecture on simulating this contract, we did exactly this creation command and exactly this initialization command in the first transaction. So I'm not going to dwell on those. This is basically what we've looked at before. And just a little comment here, if you happen to be running a really large contract, you're going to want to add the Merkleize flag to the initialize command. What that does is it's basically creating kind of a just-in-time contract on the chain, and then the .marlowe file has all the continuations of that contract, and it's done in a cryptographically secure way using something called Merkleization. So it saves you funds in your transactions, but it also actually makes it possible to run huge contracts. So just something to remember. This is a tiny contract, so we don't have to worry about that. And then we're actually going to submit the transaction. So here we go. We've basically told it that the network that we're dealing with, we've said we're going to use that ADA from the mediator. Mediator gets the change. They're going to use this signing key. We previously prepared this tx1.marlowe file in the initialize command up here. So that's basically the transaction we're going to execute. And then output file, we'll save just a copy of the actual raw transaction. Once again, you could pipe that to null or just throw it away or ignore it if you didn't want to have it. And then we asked to print statistics, and then we said wait 600 seconds for confirmation. So what we've got here is detailed statistics. So this cost about 0.2 ADA. The size was 2% of the protocol limits, and there wasn't any Plutus execution here because we're creating the transaction. And then here's the transaction ID. So once again, I'm going to copy this. We can save a little bit of typing later on. And this is basically what happened in this transaction. We had the mediator, they had some funds in their wallet. They initiated a transaction. These funds were consumed. This UTXO was consumed. And then we actually had 4, it looks like 5 outputs occur. So one went to the script, and the mediator has 3 ADA there in their internal account, and the script has a total of 3 ADA. The mediator got their change, they got their roll token, and these other people have their roll tokens, and there was a 0.2 ADA fee. Okay, so let's look at the results of this transaction. So we'll query things, and we can see at the mediator address, they have their roll token from the beginning, and then they have some ADA there. We'll look inside the Marlowe file. There's the Marlowe address, so that's where the Plutus script for Marlowe exists. And we'll query that, and we can actually see there's now 3 ADA at that script, and it has a datum hash, which is recording what the state of the contract is and things like that. Now we're going to go and do the next step, which is deposit the funds. We see that basically what we did before, we're transitioning from transaction 1 to transaction 2, and then I'm submitting this. And once again, we have to wait for it to be confirmed on the blockchain. The different thing here is that we take the input file here, the TX1, and then we have an output file, TX2. So previously we prepared the TX2. And so this transaction is basically moving us from this state 1 to state 2. And what we're doing is we're telling it, use this UTXO of Marlowe. So up here, when we queried the script address, the contract address, this is the one we found. So we're actually going to use that. We're going to be consuming that in the transaction. And then the buyer is doing the work here. So they have to provide the collateral. They provide ADA to make their actual deposit. And then they're providing their roll token to authorize things. So these are all UTXOs that are being consumed. And we'll see these in the diagram in a minute. They are signing it with their signing key. And then the output, basically the key output, aside from what's going into the contract, is they're going to get their roll token back, and then they get their change. So that's basically what we have here. We're printing statistics, we're saving a copy of this file, and you can see this is a little bit more expensive. It's about 1.3 ADA. We're at 42% of the protocol limits on this network. And then in terms of execution of the Plutus script, you can see how much memory it used, how many steps of execution it used. And so we're kind of in the low range of the protocol limits here. And the transaction confirmed while I was speaking. So we're going to record that. And then we're going to take a look at this transaction. So what happened here? So the buyer, they had some ADA, they had their roll token, and then we have this Marlowe script with 3 ADA in it, mostly in the internal account here. The transaction consumed those, and what it produced was a new version of the script that had 256 ADA in it for the seller's account. Still have the 3 ADA for the mediator, cost 1.3 ADA. The buyer got their token back, and they also got their change, but they deposited 256 ADA, so that's the difference between these numbers, basically. And we can look at this on the blockchain. Okay, so what do we see here? At the buyer address, this was a transaction, so basically here's their roll token back and their change back, and the Plutus script now has 259 ADA at it. Next step of the contract is the buyer is reporting that there is a problem. So once again, we prepare that. We see this is doing some internal payments within the script. These payments don't go outside the script. It's just internal bookkeeping. The buyer made the choice. Here they provided a time range for the validity of this transaction. And then once again, this is transitioning us from state 2 to state 3. So it's generating this TX3 output file. So when we run this on chain, which I'll get started here, this is very similar to before. We're basically saying, where's the UTXO that's in the Marlowe script? Here's collateral we're using. And we already know, like with this TX underbar 2 stuff, we know the previous transaction. So we're just consuming the 0th and the 2nd index here for the buyer because he's doing this transaction. And then the first index here, all of the same transaction hash. So this is why scripting is a little bit handy. We can just, kind of drop these in. But we're essentially consuming 4 UTXOs. Buyer's signing it again. This is the new state that we're headed towards. They get their token back. They get their change back. We're waiting 600 seconds. And here we see this is very much the same. The cost is a little bit higher. The execution was a little bit more. But basically, that's what occurred on chain. So what did this transaction look like? We had the buyer once again. They were using what they had from the previous stage. The script had their deposit in it, and the accounts were arranged this way. When they reported the problem, you can see the accounts are different now. So there's been a transition from 256 ADA here down to 256 ADA there. As I said, the fee was a little bit more. They get their change. They get their roll token. So let's look at some more detail here. You can see, once again, they got their roll token. There's their change. The script still has 259 ADA at it. And now it's the seller's turn. So we'll prepare the transaction where they dispute the problem. So we're going from step 3 to step 4. So this is the 4th transaction. And we'll execute that. And once again, this is pretty much the same as before. We're consuming the UTXO at the script address. The seller, who hasn't really been a party to anything yet, is providing collateral, providing the ADA, and using their roll token UTXO to authorize. They're signing it. They're getting their roll token back. They're getting the change back. We're keeping a record of this transaction, and we're going to print the statistics and wait up to 600 seconds. So this transaction is going a little bit slower, but you just have to be a little bit patient. It's kind of interesting. It's doing a little bit less computation. You can see the memory units and steps are a little bit lower. That makes the cost lower. Maybe it's a little bit lower on chain in terms of size. So it is important to pay attention to the protocol limits. Like if any of these numbers go over 100%, then this transaction will not run on the network. So you can kind of get an idea when you're running a contract if you're near the protocol limits or not. And in this case, for this network, we're actually quite far away from the protocol limits. There we go. So we're going to grab that. Now, if you were doing, writing a script or using a program, Python or something to orchestrate things, all of this capture of UTXOs would be, you'd probably write it automatically. For this demo, I'm just doing copy and paste. So the 4th transaction, very similar. It's just that the seller is playing the role here, and they're disputing a problem. You can see the internal accounts actually don't change in the script. And once again, people get change. They get their roll token back, and they're paying a fee. So we'll look at a little more detail here. You can see the 2 outputs, and then the script address still has 259 ADA. Now it's the mediator's turn. So he's basically making the ruling, and he's making the ruling for the seller. So the seller is going to receive funds. We saw this in the previous lecture segment, how there is a internal transfer between accounts. There's an external transfer of the funds to the seller account, and then there's also a external transfer of the minimum ADA that the mediator originally deposited. So there's going to be a lot more activity here. We're running this transaction. The format of the transaction is basically the same. We're just doing this kind of daisy chaining of UTXOs, except here we're using the mediator, UTXOs, the mediator signing it, and getting their token back, of course. So this one ran fast, so we're going to grab that hash for the transaction ID, keep a record of it, and take a look at what went on. So once again, this is very much the same on the consumption side, but now we have something interesting on the production side. So there's no output to the Marlowe script anymore because the contract is closed. All the funds have been dispersed from it. So no Marlowe script, but instead we have two outputs to the payout script. So one is for the mediator, it's the 3 ADA. Another is for the seller, which is 256 ADA. And so we're going to move forward. Okay, so let's look at the more detailed results of this transaction. And there we go. The mediator, they have their outputs from the transaction. Now they don't have their payments because that's in a separate address. Similarly, we can see that the contract really did end. So there's basically nothing at the contract address. And so, like, where did all that ADA go? We're going to compute the role payout validator address. So that's this. And then we're going to query it. And so, lo and behold, you see there's 3 ADA there, and there's 256 ADA there. If you computed the hashes, you would actually see that this hash says pay to the mediator, and this hash says pay to the seller. So in the previous example, we only went to this stage, but now when we're running on chain, we have a little bit more to do, which is to get those funds out and back to people's wallets. So the new command here is called Marlowe CLI run withdraw, and it I'm going to just start that up now. Basically, you say who's doing the withdrawal. Here's the Marlowe file that had the payments, and then this is what we're putting in. So the seller is basically going to throw in some ADA, throw in some collateral. This includes their roll token, and then they're going to sign it. They want their roll token back. Change goes to this address. Basically, everything's going to go to that address, and then we're keeping a record of this. So here we see this ran. These are actually less expensive transactions. This is about 0.4 ADA, only 8% of the protocol limits in terms of transaction size, and it's a tiny bit of Plutus execution. So let's grab the hash for that. We'll look at this transaction. As I said before, they're providing some ADA. Some of this is used for collateral. Their roll token, they're consuming what's at the payout script. So that had 256 ADA. And then they're paying the fee. They're getting their change. They're getting their 256 ADA, and they're getting their roll token. And so we're going to actually just do the same for the mediator. And in this case, they're going to be withdrawing just the 3 ADA that they put in at the very beginning of contract creation. So I'm going to grab that hash. And we'll look at these transactions. It's essentially identical to the 6th transaction, except now 3 ADA is involved, and it's going to the mediator. So let's take a peek here. First of all, payout script is empty, so it's paid out everything. We go look at the mediator address. You can see they have their change, the 3 ADA that they were basically receiving from the contract payout. And then this is their roll token. And then at the seller address, same story. They have some change. They have their 256 ADA that they withdrew from the payout. and then they have the role token. And it's kind of convenient to sort of clean things up here. So we're actually going to just use one of the kind of utilities in Marlowe CLI to clean up all these UTXOs, send them all back to the wallet so that these addresses aren't just sitting with ADA that was used in the demo. So we sent that back. And then we can actually look at the Cardano blockchain explorer. So let's just take one of these and see how this goes. Okay, so there's the transaction. So you can see this really did occur live on the blockchain. You can look at things like here's the one of the role tokens. I don't remember. I think this is the buyer situation. So there's the buyer address, policy ID. You can see things moving in the script address. You can click on the script address. We see there were 5 transactions, which is correct. And then here's one of the last transactions where it did one of the payouts. So if I click on that, we can see, maybe not. I thought we could find, well, if we click around enough, we can find the role payout validator. But I could leave that as an exercise for you. So anyway, we have basically run the whole contract on the blockchain. So now we've learned how to simulate it and actually run it. And I think before we showed you this UTXO diagram, maybe this makes a little bit of more sense because we showed you fragments of this as we did each transaction. Now you can see the whole thing. So, as this loops, we see we started with 3 UTXOs. We basically did the creation transaction, did the first buyer deposit transaction. Buyer reports a problem. Seller disputes the problem. Mediator makes the ruling for the seller. Mediator withdraws their funds. And this was the mediator withdrawing, and then the seller withdraw. So basically, that's the sequence. I should say this is a little bit inaccurate at the very beginning because we had minted the role token separately, and this diagram actually shows them being minted at the same time, but that's sort of a minor difference. Now, troubleshooting. There's a lot more going on here, so there are more things that could go wrong too. First of all, make sure that the simulation works. So you can look at the previous lecture segment. If you have a large contract, make sure you Merkleize it, because if you create a really large contract, it's just not going to fit on the blockchain. And now, in the simulation example, we had all these errors that could occur. These could occur on-chain too. If you've done proper simulation and stuff, that shouldn't happen, because you should never really get to the stage where you'd make an on-chain error, but you can circumvent that in various ways. But there are also things that could occur on-chain that wouldn't occur in simulation. So things about account balances, if the script was garbled, like the script datum, like you were running 2 contracts and you got them mixed up or something, you might get this B1 error. Merkleization problems are reported. Basically, all the Plutus related things that could go on. And then Marlowe, checks, the Marlowe validator checks to make sure, the right funds are going to the right places. If the clocks are off, you might get, other errors. So these are not things that you should routinely see, but if you're experimenting, then, you should be aware that there's sort of a cheat sheet to decode these. And then there are also deeper errors that you get from Plutus or from the node. So resources, it's pretty much the same as previously, except the debugging cookbook contains information about debugging on-chain problems in addition to simulation and other things. So that's sort of a special resource. And then exercises. So these exercises are a little bit harder than the simulation ones. So one thing you could do would be, as we before had an exercise to do simulation where you mess things up so it doesn't work, once again, you could do that with the execute command. So maybe leave out one of the UTXOs or put the wrong token or the wrong signing key in, and then you can see what happens. Fiddling with the time ranges is another good way to make things wrong. You could repeat execution of the escrow contract on chain, but confirm the problem, have the seller confirm the problem instead of disputing it. So we'll get a different execution path. You could run any of the other template or playground contracts. And, if you don't really want to get into all the on-chain stuff, one thing you can do is just draw a UTXO diagram for one of the contracts you've run. So you could do that, for instance, use Marlowe Run to run a contract, or even use Marlowe Playground to run a contract, and take notes and actually draw a diagram of what would be happening with all the UTXOs. So those are things to try. Once again, these are optional and they depend really on your learning objectives. So in summary, we saw that roll tokens have to be distributed for parties to use a Marlowe contract. There are some exceptions to that, but the standard use case has roll tokens. We introduced the execute command, which actually submits transactions for progression of a Marlowe contract. And then the withdraw command submits the transactions to withdraw funds from the payout script address. And if your contract is large, use the Merkleization flag. And then you can always view things on the Cardano Explorer, or if you're using keys derived from an actual wallet, you can use Daedalus to kind of look at all the transactions. So thank you very much.